Okay, so this is the second part of this section. Um, we're going to go through quite a few examples. I'm going to fly through the examples, um, slow down, and rewind and go back and take a look at the ones that you feel like you need to see again. Um, but a lot of them are kind of similar to each other, and so I just want you to get used to different wording and see kind of help you choose what formula you should use depending on the wording of the problem. Okay, so we have three new terms this section. First one's factorial. I think a lot of you know what factorial is. I showed it in yesterday's video. Factorial, again, is just the product of all positive numbers from one to a number. The symbol for factorial is the exclamation mark. So when you're doing 6 factorial, it equals 6 times 5 times 4 times 3 times 2 times 1. Okay, we use that quite a bit. Permutation is something that you may be familiar with, you may not be, but it's an arrangement of objects, this is key, in a specific order. So this is where order matters, all right? Um, the formula for it, oh, sorry, one important thing to remember about factorial is 0 factorial is equal to 1, okay? 0 factorial is equal to 1. Permutation. The way it's written is this. You have a little number, and then a big P, and then another little number. And the formula for it is n factorial divided by n minus r factorial. The good thing about this, I'm not going to make you memorize this formula because your calculators can do it for you, and almost all of your phones can do it for you. Tomorrow in class, I will show you how to do this on your calculator, and we will find it on your phones. But for right now, this is the formula for it. It lends itself to the counting problem, the counting rule from yesterday very well, and I'll show you that in our examples. So again, this is permutation. This is when order matters. The next one, combination, is grouping objects just like permutation, but when order does not matter. So for instance, permutation may be like how many different ways can 10 people take first, second, and third? First, second, and third, that's order matters. They're three distinctly different labels, if you will. First is different than second, second's different than third. If we just said how many different ways can we pick 3 people to go on a trip out of 10 people, that would be what's called a combination. The order doesn't matter. They all 3 get the same thing. Because of that, we have this little bit extra r factorial, and that takes care of making sure that the order doesn't get counted. Okay. In both of these, this represents n things taken r at a time. Okay, n things taken r at a time. And again, we'll show you that when we get into the examples. Okay. So here we go. Suppose a business owner has a choice of 5 locations in which to establish her business. She decides to rank each location for certain criteria, such as price of store and parking facilities. How many different ways can she rank 5 locations? So the first thing that you should ask yourself is, does the order matter? If she's ranking 5 locations, is there an order to it? Well, when ranking, the answer is yes. There's a favorite, a second favorite, a third favorite, a fourth favorite, and a fifth favorite. This could be something as easy as just doing your counting rule, like from yesterday. 5 blanks. And you have 5 choices for your first choice, then you only have 4, then you only have 3, then you have 2, then you have 1. You multiply those, that's 120 different ways, right? Or you could think of this as a factorial. 5 times 4 times 3 times 1 times 2 times 1 is 5 factorial. Or the last way is you could use permutations. And the way to think of this is you have 5 things, you're taking 5 of them at a time, and order matters. That's what makes it a permutation. Either way, you get 120 for your answer. Permutation and the counting rule go very, they kind of go hand in hand. Okay, suppose a business owner wishes to rank only the top 3 of the 5 locations. How many different ways can she rank them? So again, you could say first choice, second choice, third choice. You have 5 for your first, 4 for your second, 3 for your third. Or you could say it's a permutation. We have 5 things. We're taking 3 of them at a time. Order matters, so it's a permutation. And when you plug that in your calculator, you get 60, same as up here. I'm going to show you the formula real quick, okay? Because this is where the formula comes from. If you think of this, n factorial, that's 5 things. If we write that out, that's 5 times 4 times 3 times 2 times 1. Okay? And then if you do the bottom, 5 minus 3, that's 2. 2 factorial is 2 times 1. These cancel each other. And you notice your answer is just 5 times 4 times 3, which is exactly the way that the counting rule worked. So that's where this formula comes from. Like in the previous one, we had 5 factorial divided by, like we were picking 5 at a time, right here. This one would have been 5 factorial divided by 5 minus 5 factorial. Well, you end up with 5 factorial divided by 0 factorial, and we know that 0 factorial is just 1. So it's the same as this. So that's how that permutation formula works. And next up, television news director wishes to use 3 news stories on the evening show. 1 story will be the lead, 1 will be the second, 1 will be the closing. If the director has 8 possible stories, how many possible ways can the program be set up? So again, does order matter? That's the first question you ask yourself. Since order matters, we're looking at a permutation or just a counting rule problem. I would suggest kind of getting, it's kind of, I guess, either way. If it's as simple as just, if you can draw, here, we got 3 blanks, right? We got a lead, a second story, a third story. We have 8 choices for our first one, then we only have 7, then we only have 6. That's about as easy as you can get. But if you get into the habit of just thinking, I'm going to use either permutation or combination, that's fine as well. So here we have 8 things. We're choosing 3 of them. Order matters, so it's a permutation. When you plug that in your calculator, you get 336. It would be the exact same as what I did above. School musical director can select 2 musical plays to present next year. 1 will be presented in the fall and 1 in the spring. They have 9 to pick from. How many different possibilities are there? Does order matter? Is it different showing 1 in the fall than in the spring? Yes. So we're dealing with permutation. We're picking 9, we have 9 things to choose from, and we're picking 2 of them. So 9 permutation 2 gives us 72. Again, I'm going to go through these examples pretty quick. You can go back, look at them again, write down questions if you have any that we can go over in class tomorrow. Newspaper editor has received 8 books to review. He decides that he can use 3 reviews in his newspaper. How many different ways can these 3 reviews be selected? Does order matter? Is there anything in there about being a first review, second review, third review? Anything about importance? First review goes on the front page, second review goes on the back page. Is there anything like that in there? And the answer is no. So the order does not matter. So because of that, we're going to use a combination. So your combination is, we have 8 things, we're choosing 3 of them, order does not matter. When you plug that in your calculator, here's your formula for it. You got 56. So just 2 different looks at it. Don't be too worried about this one. That one's just confusing. In a club, there are 7 women, 5 men. committee of 3 women and 2 men is to be chosen. How many different possibilities are there? This is where things get a little bit tricky. You have to choose a committee of women and men. Okay, that key word. And remember the symbol that we use for and is multiplication. So what you're actually doing here is looking at this as 2 separate problems. 7 women choosing 3 of them. Okay? Does order matter? Does it say anything about order mattering? It does not. Okay? There are no separate roles. They're just in a committee. So we're using a combination. So to find women, we're using 7 women. We're picking 3 of them. Order doesn't matter, so it's a combination. So there are 35 different ways to choose the 3 women. For men, we have 5 men. We're picking 2 of them. So there are 10 different ways of picking the men. Think of it this way. If you had the women part, and you had 35 in a tree diagram, you just kept drawing 35 of these, right? Each one of these would then have 10 different men that could be selected. So 10 here, 10 here, 10 here, 10 here, 10 here, 10 here. 35 separate 10s. So how many total would there be? You just multiply them. Okay? And is multiply. So you go 35 times 10. That's 350 different possibilities. Okay, so again, when you're looking for 2 separate things, right? How many different women? How many different men? They're multiplied because it's an and. If it was an or, we would probably be adding them. Okay? We're going to get into these counting rules, combining them with probability rules. Not too much changes, except that we're usually doing one over another. Okay? So real quick. The store has 6 TV graphic magazines and 8 newstime magazines on the counter. If 2 customers purchased a magazine, find the probability that one of each magazine was purchased. Okay? So the TV graphic, 1 magazine of the 6. The newstime is 1 magazine of the 8. Total, you got 2 magazines of the 14. So what we're looking for is, this is what we're choosing, right? We're choosing 1 out of the 6 for TV graphic. We're choosing 1 out of the 8 for news time. We have to choose one and the other, a TV graphic and a news time, so we're multiplying them. And then total, how many total magazines do we have? We have 14 total magazines. We're choosing 2 of them. So this top is what we're looking for. The bottom is the possibility, like the possible number. So we get 48 out of 91.